So welcome back, everybody. So today is the second lecture out of the mini lecture series on hydrodynamics. As promised, today I want to sort of talk about hydro as effective field theory. And the way that I sort of want to do that is basically by analogy with the sort of simple example of diffusion that we did yesterday. And pretty much all of the things that we discussed yesterday will have an analog in hydrodynamics, but there will be sort of extra sort of complications that will arise. So just to sort of reiterate, so yesterday we talked about diffusion. The sort of central object for diffusion is some charged current, can be, for instance, an electric current, could be a mass current, something like this, that is conserved. So it obeys a conservation equation, V mu, J mu, 0. And what we want to sort of, what we did yesterday was that we constructed an effective theory of how essentially a charge sort of evolves as an initial value problem by sort of writing down a sort of expansion of this current in terms of its zero component, the sort of the scalar charge that we have in the problem, plus gradients and gradients. So already at the end of yesterday's lecture, I started sort of laying out the sort of strategy for hydrodynamics. So there, basically, the object that we want to talk about is the object that is associated with energy and momentum conservation. So basically, it's the energy momentum tensor T mu nu. The energy momentum tensor T mu nu is conserved. Energy and momentum are conserved in the theory. And you want to sort of build up an effective theory by sort of writing down the energy momentum tensor in expansion of the individual components. And okay, over here we had one scalar quantity, for instance, the electric charge, that was our building block. Here we have a Lorentz vector, the form momentum, or for the energy density, or the energy and the momentum. Basically, the way that this is structured is that we sort of write it in terms of a scalar quantity, the energy density, and some 4 vector u mu, which is sort of like the momentum density divided by a dimensional 4 quantity, and we sort of substitute the fact that this would now be 5 degrees of freedom, sort of substituted by a constraint on this vector here that says that the square of the velocity has to be -1 in my units here, but the metric here is mostly plus.
All the pen doesn't show up on the screen.
Try a different one. This is the one that I should not use. Maybe let's try this. And gradients. Is it better? Okay. So that's the strategy. And pretty much we sort of are going to follow the same recipe as we sort of started yesterday. So over here in diffusion, we sort of said that we want to write the current in terms of gradients of the number density, and we said that, okay, we start by first order terms here. So this is J as a first order gradient on the number density as a first entry, because at 0th order, this is a vector, and we can't really write down anything in terms of the scalar charge density n. Over here, the situation is sort of similar in the sense that we write down everything that sort of is allowed by the building blocks, but unlike the case of diffusion, there are terms that contain no gradients that we can write down contributing to the energy momentum tensor. And last time we would have said, okay, if you want to write down the energy momentum tensor to sort of leading 0th order in the gradient expansion, we have as our building blocks the energy density and this vector u mu as our building blocks, and we want to construct a rank 2 tensor with Lorentz symmetry. So basically what you can do is you can write a function of the energy density times the symmetric combination of these vectors here. That will be one term that you can write down, contains no gradients, and contributes to the energy momentum tensor. again, taking our inspiration from our example of diffusion from yesterday, we found that besides the fact that we can write down gradients of this scalar electric charge density here, the formalism sort of naturally sort of leads to additional sort of terms or contributions in the expansion. And in the case of electric charge, these are sort of easily motivated by saying that if you have a moving electric charge, it's natural to also include the associated electric and magnetic fields in the description. So really, we find that we have to supplement our building blocks by sort of adding basically the vector potential and the electrostatic potential to this game here. And that means that at first order ingredients, I get also terms that sort of include, for instance, the electric field as the first order derivative of the corresponding potential, basically. By analogy, the corresponding construction on the energy momentum tensor says that if you have, if you want to study the dynamics of energy and momentum, that naturally sort of leads to basically the idea that you should include gravity, gravitational waves in your description. And as such, then this says that the analogous object to the potentials in the case of electric charge is basically just the metric tensor T mu that you should include in your construction. So while at the level of the electric charge diffusion, the contribution from the electric field only enters at first order in the description here. For the energy momentum tensor, there is a term that contributes to the metric directly without any derivatives, and we can sort of introduce it, simplify it, multiplying it with another function f2 that also can depend on that. So just to sort of review the nomenclature, I call this the first order current because it contains first order derivatives of things. By analogy, this thing here would be the 0th order energy momentum tensor because it contains no derivative of things. And we will talk about how to include sort of derivatives in the next step. But right now, let's just focus on this 0th order approximation that we've been writing. Are there any questions on the strategy up to this point? Is this classical? Yes. Yes, it's classical. But it's only classical if you want in terms of ignoring correlation functions. It is not classical in the sense that there can be H bars hidden in all of these transport coefficients. Yeah, no, I'm not yes, but the format is it specifically sort of ignores the fact that there can be sort of higher point quantum correlations of these operators. Yeah, it's basically sort of saying no, we neglect those because we sort of are aiming for a classical bulk description of the system. Okay. So now let's maybe sort of explore this a little further. One thing we have to say is that, so I said that this object here is the energy density. Really sort of what that in some sense implies is that if I look at this energy momentum tensor, there's one thing that I know about, which is that if I am in a system that is not moving, so just sitting there, if I take the 0,0 component of the energy momentum tensor, that's the time-like component, that is nothing else but the Hamiltonian. So its expectation value should be the energy density. It looks sort of more, maybe it looks more unfamiliar in this form here because there are these vectors u over here, but we can sort of do the following. We can use the fact that we've normalized this vector here in such a way to sort of say that, okay, if we take the projection of this 0th order energy momentum tensor with u mu, then what we get is we get from this term here minus f1 epsilon u nu plus F2 mu nu. And what that says is that, okay, we sort of projected this out onto basically a vector that's sort of time-like. Maybe sort of to make this even more apparent, we can also sort of just project this once more with another vector u nu. So we do the fully contracted energy momentum tensor. Then this gives us a minus from contracting the mu indices. This gives us a minus from the nu indices. So we just get F1. And this gives us u and mu contracted, which just gives minus F2. And this object here is nothing else but the time-like component of your energy momentum tensor, which in the local rest frame is nothing else but x. So this suggests that, okay, writing it in this form may not have been the best way to doing things. So one way of writing it differently, okay, so this combination is basically the energy density, and we can sort of write it out in such a way that the sort of energy momentum tensor here, one combination of these two is basically the energy density, and we can look at the other. Yes.
So the question.
Yes.
Can you please explain again how the metric is included in the mu?
Can you repeat the question?
Can you explain how the G mu nu gets included in the G?
Okay. Yes. So, okay. There are various ways to sort of get at that. What I sort of just said was basically by analogy with the case of moving electric charges needing electromagnetic potentials. Moving masses, moving energy and momentum sort of basically necessarily generates gravitational waves. So that's one way to see that you should have a metric tensor in the construction. A different way, a more formal way, would be to say that, okay, over here, the sort of partition function, or the log of the partition function sort of includes an integral d4x of the effective action, which sort of couples the object you're interested in, the current, to some source a mu. The same thing over here says that your partition function basically sort of goes as the object you're interested in, t mu, coupled to its source, and the source is the energy momentum tensor. So that sort of says that when you sort of want to write down an effective theory for the energy momentum tensor, a consistent way of formulating it is by going to a theory that sort of has a non-trivial metric, meaning you turn on gravity, basically.
So is it correct to say that in the case of diffusion, including different fields for it was not a necessity? But in this case, it's a necessity because you have included the concept of norm in the plane.
So I would argue it's necessary for the consistency to include them in either case, because once you calculate correlation functions, otherwise the theory is not consistent. So I would argue you have to include the sources in both of these cases. It's not a choice, it's basically required. Okay, good. So that sort of gives us one contribution for these energy density, and then we can sort of rewrite, for instance, this expression here, such that we get a contribution that says, yes, let me rewrite it in such a way that I subtract and add F2 to this first term here. So then this is F1 minus F2 mu plus F2 mu, which is this term here, and then I have to stuff this term I subtracted. I have to add it back in, so I get plus mu over here, and I sort of use that construction because then I can sort of read off the energy density as the first term in this expansion, and then the F2 here is simply some other term that appears in the energy momentum tensor. And maybe sort of the most straightforward way to sort of figure out what that is if we actually sort of do the exercise and consider for a moment, let's call it fluid at rest. So I said that this is some 4 vector here. If I have a fluid at rest, that basically means that the fluid is not moving. But this 4 vector has only a 1 in the time-like direction and 0s everywhere else. If that's the case, we can look at what this energy momentum tensor actually looks like. The first part here is just the direct product of this vector that only has a 1 in its time-like component. So in the fluid rest frame, P mu 0 local rest frame has an epsilon in the time-like component here. And let's stay at this combination here a little bit. And because I'll sort of use that further on, I'll sort of call it delta mu nu. This delta mu nu has exactly the same combination u mu nu in the time-like component, but it's added to the metric tensor, which in my sort of convention has mostly pluses. So it's 1, 1, 1 in this space-like diagonal, but it has a -1 in the time-like component. And the -1 from this metric together with the +1 of this means that this is a 0 in this component, so that the delta mu nu in the local rest frame is just given as 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1. So it is, if you want, so a co-moving space-like projector. Projects on just the space-like part, but it's written in the covariant way. By contrast, the u nu is the one that projects on the time-like part. So it's a co-moving time-like projector. And this is useful because well, maybe we sort of want to sort of divide up things into things that are time-like and space-like for further use. Coming back to my energy momentum tensor, sort of, if I know that this is the form of this delta here that multiplies the F2, and this is my epsilon here, it means that I will have 0s everywhere except for the diagonal. And in the diagonal, I have this function F2. So basically, let me write this down and then erase it again. So we have 0s almost everywhere except for this diagonal here. Yeah. And in order to sort of figure out what the F2 is, there are various ways. One of the ways is that you just calculate directly, for instance, Txx, the xx component of your energy momentum tensor, and you find it's nothing else but the minus the free energy of the system or the pressure. You can do the calculation, for instance, in field theory, and that's what you find. So F2 here is the pressure of the system, so that your energy momentum tensor in the local rest frame has this particular form. So here we have a fluid that has, so we've sort of done the approximation where we've thrown away all higher order gradients, and it will turn out that this is a fluid that's, for instance, imperfect thermal equilibrium. Local. Yes, perfect local equilibrium. We can have some global gradients, that's fine, but locally, this is the form of the energy. But this is sort of getting ahead. We'll get to sort of the relations when we go out of equilibrium in a moment. There's my erase. So once we have this form of this energy momentum tensor, let's just store it somewhere. T mu 0 is epsilon u mu plus p delta mu nu. Then we know that if we sort of work in this order of approximation, we can sort of look at the conservation equation for the energy momentum tensor. D mu T mu nu 0 is 0. Because now we have one contraction here, but there is an open index nu. So we have 4 equations in covariant form. Again, compare that with the diffusion equation, which was just one equation. So it's conceptually the same as the diffusion equation, but it's more complicated because it has more components. So one way of sort of splitting up this equation is that we take projections on the time-like and the space-like part. So for instance, we can look at u nu, d mu, t mu nu of 0. And well, what do we get? So we get u nu d mu epsilon u mu u nu. Then we have a term u nu epsilon d mu u mu u nu, and then we have a term plus yeah, let's write it down. D mu p u nu delta mu nu, and then p u nu d mu delta mu. So far so good. Let's just observe that here we have a term where I have a contraction between the time lag u and the space lag delta. So this always projects to 0 because you have a time lag on a space lag that doesn't sort of give anything non-trivial. That's just 0. What else do we have? In here we have the derivative acting on the projected delta. Again, let me write that out here. I might need this more often. So if you have a derivative on this, the derivative on the metric is always vanishing because it's a covariant derivative. The derivative on this may not be vanishing, so this is basically the only contribution you get. So we can erase this part here simply by u mu u nu. And then this part here looks an awful lot like that term over there, where the only difference is that you have an epsilon here and a p there. So long story short, these two terms sort of can be combined, and then you get one extra term from here, where you can see that, okay, the u nu together with the u just gives us a minus sign. So let's just do that. The minus sign here. And from these two terms, so this term vanishes, we said. That term here just adds a p to the expression. So we get epsilon plus p u nu times this expression. And we can sort of figure out what that is if we have a contraction of that. Let's do it slowly. So if we have d mu u nu, d mu u mu u nu is the same as u nu u nu, d mu u mu plus u nu u mu d mu u nu. And that second term here involves, the second term here is the same as u mu u nu d mu u nu, but that's the same as 1/2 d mu u mu u nu, which is -1. If you take the derivative of -1, it's 0, so that term just goes away. So you only have this term left, and sort of similar to what I said before, I will sort of use notation to sort of express quantities that sort of appear every once in a while. So for instance, we have here a quantity that basically is, okay, now in this case, that's fine. So what I want to sort of introduce is, here I have a combination of u mu d mu that's acting on epsilon. So there are operators that look like this. U mu d mu, which in local rest frame means you're taking the time-lag part of the gradient. So I will call this thing d, and it's sort of like a time-lag derivative. So think of d by dt for this thing. It's just in a Lorentz covariant way, it's a time derivative. And just for
d by dt, if you interpret t as the time in the local.
Exactly. Yes, that's what it is. And by analogy, we can also define a locally co-moving space-like derivative, and we have to use the space-like projector for that. So then this would look like this. For instance, the mu alpha, d mu, which I denote by d alpha with a perp, and this is sort of space-like. And you notice that in the last, I don't know, 10 minutes or so, all I've done is written down tensor indices, which is one of the reasons that I wanted to do diffusion first, because it has all the physics, but none of the complications. So now we have the same physics, but a lot of writing to do. And I sort of am very sort of detailed with all my indices. I will sort of skip you the details as we go on, but I wanted you to sort of see that this is actually exact and there's no hand wavy things involved. It's just, you have to sit down, think about it carefully, and this is how you sort of define it. Okay, at the end of the day, what do we get? So I said that I want to replace this by d epsilon, and then we have this combination here, which just involves this here, which is -1, and the derivative of u. So long story short, you get that this is the same as minus d epsilon. Let me sort of write it differently. We put the minus on the other side. So that means that this equation means we have d epsilon plus epsilon plus p u mu 0. So that's one of the components of the conservation of the energy momentum tensor, assuming that our effective field theory doesn't have any gradients inside. It's 0th order fluid dynamics because there are no gradients in the energy momentum tensor. And unlike the case of diffusion, who remembers where I said you can write down 0th order diffusion, it doesn't give you an interesting theory. Some people are nodding. This theory has a lot of interesting applications because this is nothing else but the relativistic version of the Euler equation. So this, should I say this, are the relativistic equations. Just for completeness, this is just the space-like part. Sorry, this is just the time-like part. We can also look at the space-like projection of this. And I will spare you the details. It's really just tensor algebra. Looks exactly the same way. And what you find is that there's an equation that looks like this. Plus, so we have to sort of make sure that my sign conventions are correct. We'll go back. Right. Like this. Epsilon plus p u alpha plus, and what you get here is the space-like gradient on the pressure, and it is customary to sort of rewrite that in a form where you sort of say that, okay, it's the derivative of the pressure, so this is dp by d epsilon times the space-like gradients on epsilon. And this combination dp by d epsilon, that is sort of a quantity that is a transport coefficient of whatever fluid you're considering. And sort of with hindsight, we sort of can recognize this to be the speed of sound squared. Okay. Cs squared. So basically, you find that this equation here always is, well, often is expressed in such a form. So these are the relativistic Euler equations. And if you sort of think a bit, what we sort of put in there, we said that, okay, if you want to have an effective theory description, expansion of the energy momentum tensor, we use symmetries, and we use the fact that we have conserved quantities such as the energy, a scalar, and the momentum, a 4-vector. And we get out most of cosmology, most of astrophysics. In the low energy limit, which we can do in a moment, we get essentially all studies of turbulence. These are all in these equations, okay? So we get a lot of physics from very, very minimal input. We never had to say that, okay, we have these particles that scatter with each other and they have a collision kernel that sort of has this complicated integrated form. No, none of that. We just say, okay, this is the universal description of all forms of matter in the low energy limit. That's the beauty of it. Okay, just for fun, let's do the following. So if we take the non-relativistic limit, NR limit, what does that mean? Well, so in general, I said that this thing is some sort of velocity. If you sort of have taken a course in special relativity, you know we can write this as the Lorentz gamma factor times a vector that has this form. It says 1 in the time-like component and the usual sort of 3 velocity in the space-like component. And if we take the non-relativistic limit, we assume that v here is much smaller than the speed of light, which in my units is 1. So we expand everything in v. And if we do that with this first equation here, we find that, okay, here we have our co-moving v. What does that look like? So u mu d mu is the same as then gamma dt plus v dot usual grad, but we expand around gamma is 1. So basically, this is approximately the same as dt plus v dot L. So then this equation here becomes something like dt epsilon plus v dot grad epsilon plus epsilon plus p. And here we have the derivative of u. So that is the same as dt gamma plus gradient of velocity. Dt gamma, the lowest order is gamma squared, so it's sort of higher, or v squared, it's higher order than the velocity p. This is sort of approximately 0. We only have to keep this term here. So we find that this is the non-relativistic limit of this part of the relativistic order equations. It's really the continuity equation. And you can sort of see it more clearly by sort of also realizing that in the non-relativistic case, you want to split the energy density into rest mass and kinetic part. You're going to split epsilon to be, I'll write this as mc squared, okay? Assuming that you know what I mean by this, I sort of separate out the mc squared, which is the constant mass part, plus the kinetic part, which I call rho. And because I have this mc squared in here, the epsilon is always much bigger than my pressure in the non-realistic limit. So I can neglect the pressure whenever it comes in with a sort of plus or minus sign with respect to the energy density. So that means that this equation here really turns into dt rho plus v dot b rho plus rho times the gradient of v is 0, which is nothing else but the usual non-relativistic version of the continuity equation. Yes?
The state expansion rate will also drop the term gradient gamma.
Yes, that's right. Yes. Yeah, all gradients of gamma are order v squared, which are beyond the leading order non-relativistic limit. So I'm just doing this to sort of say, okay, these really are the standard equations of fluid dynamics, Euler equations. They're just written in relativistic form, and as such, they sort of apply both to systems that have small fluid speeds as well as large fluid speeds. Questions up to this point? Yes, you're.
More common, I guess, if you're also assuming that not only these small, but it kind of remains small throughout the evolution of the system. In other words, accelerations are small as well.
Yes, that's true.
Yes. Because that's what you just need to show gamma.
Yes, I'm assuming that v is always much smaller than the speed of light throughout the entire evolution. If I take this non-relativistic.
Can you say, I think that one, can you say again what is the approximation of the energy density?
Oh,
I mean,
sorry.
this doesn't work by units, although
That's right.
You multiply with some higher.
Yes. So let's call this rest energy density. So basically have, in the non-relativistic limit, you usually have non-vanishing particle masses. So they give you a rest mass energy that leads to rest mass energy density. And this is taken out if you want to sort of make connections to the usual non-relativistic literature, because you're really not interested in what the rest mass energy is doing. It's just unchanging and constant, and it's basically a constant that you take out. And all you're interested in is the kinetic energy density, which is basically what's appearing in, if you open up Landau-Lifshitz, that's the quantity that energy density really sort of means. It's the kinetic energy density.
Assuming that the particles are
I'm not assuming that there's any, I'm not making any assumptions on the interactions at this point. Of course, eventually we'll figure out that what I'm sort of, eventually what I'll, if we sort of carry this program further, which we'll do in a moment, we'll figure out that the corrections to these approximations are small, provided that the interactions are very strong. So this works best if we have a strongly interacting system. It works not so well if the interactions are actually. Right, but what I'm saying is that this non-relativistic limit applies even if you don't have particles. You might have some condensed matter system where there are excitations that are something, you don't know what they are, but they have kinetic energy. Okay? So they have kinetic energy density, and I'm claiming that their dynamics will be described by the non-relativistic limit of the Oil equation. Because I never had to assume that weak interactions are part of the process.
But you do assume that the mass is constrained. That means
right.
whatever strong coupling you have, it cannot be strong enough to create.
So I assume that there is some mass conservation. Yes, that's right. Yes. Yes.
So you get a 10 particle from volume, and total energy is not the sum.
So I think I didn't quite understand. So you say you have 10 particles in a volume, and yes?
And then the energy in that volume, the sum of the individual energy of the particle.
The sum in the volume is, yes. I mean, if you have particles, that would be the case. Yes.
They interact. What about they interact?
Oh, you're saying that, okay, you're not, okay, fine. So yes, they're not non-interacting. So you have, at this level, there is no mention of particles. Okay, so it's just saying that in a volume, you have a certain energy, and it would be composed of some rest mass energy, which is assumed to be constant, and kinetic energy. And that can be the kinetic energy of your 10 particles suitably corrected for interactions, or it can be some other form of kinetic energy of some glue modes that sort of do something, right? No, it does not.
If you have some glue that is strongly
right.
bound,
yes.
then the total energy of that system is lower than the rest
right.
mass is some of the rest mass.
Okay, so I should be careful. So I call this kinetic energy, but really what I mean is it's the difference between the actual energy density minus rest mass. Right. Thank you. Further questions, comments? Okay, good. So fine. So we get most of fluid dynamics, but we have only started the sort of setup of the effective field theory description. So we've only sort of written down the leading order, 0th order contribution to the energy momentum tensor. One of the key things that sort of you might ask about this construction is, okay, fine, you get the Euler equation, you can describe all sorts of nice physics. Do you know when your description breaks down? And the short answer is, on this level, no, you wouldn't know, because you don't know what the corrections are, so you have no idea whether the answers you get at any scale are to be trusted or not. So you want to sort of look at what corrections are, how large they are in what regime, to be able to sort of quantify, well, the Euler equation really is a good description of, I don't know, process X at scale Y. Okay? You need to look at what the corrections are. So let's do this, corrections to 0th order hydro. And by the way, let me sort of spell this out once more. So 0th order hydrodynamics, ideal fluid dynamics, and Euler equations are all synonymous. They're all the same thing. And equilibrium hydrodynamics. They all describe the same equations. Their name sort of comes in different contexts, but they're all the same thing. So we're going to look at corrections to those. Obviously, what we have to do is we have to write down corrections to the energy momentum tensor, and we want to write down all corrections that contain exactly one gradient of our building blocks, the energy density and the full velocity mu, and nothing else, in the sort of EFT setup that we sort of successfully used also in the diffusion. Now, okay, what does that mean? Well, what can we write down? We can write down things that involve gradients of the fluid velocity suitably symmetrized. So for instance, we can write down terms that have, so there's a term that sort of looks like this, sigma mu nu, which can be d mu u nu plus d mu u mu minus 2/3 delta mu nu d alpha u alpha. And you can also write down a term that, for instance, looks like this, delta mu nu d alpha u alpha. Okay. So these are two possible terms that I can write down, and I will write down those. So let me start write these down. So there's the sigma mu nu.
Derivatives to be spatial, or
in this case, yes, right. So very good. So let's do all of these. Let's sort of use all of these to be spatial. It turns out that in practice, in this case, let's just keep it. So yes. So basically, by the same process that we discussed in the diffusion equation, there's an ambiguity on how you count time and space-like derivatives. In the case of the diffusion equation, one time-like derivative was worth two space-like derivatives. In this case, because we have the Euler equations as our leading order sort of setup, there one time derivative counts as one space derivative. So there's a one-to-one matching. You have to make a choice which ones are the independent components. And sort of by analogy, we use the space-like gradients to be the independent building blocks. So as Ule sort of remarked, really I should be writing down space-like deltas for all of these constructions because these are my independent building blocks. So we have this guy here, and then we have delta mu nu d alpha, and both of these come with coefficients. They're usually sort of called eta and zeta, and these are transport coefficients, similar to the diffusion constant or the speed of sound. They are called the shear viscosity and bulk viscosity, respectively. And they're called this because the way that I sort of split up things is, you note that in this thing, the sigma nu, which is called the shear stress, there's one term here that I sort of, that looks like the one that I sort of write in the bulk sector. That's intentional. It's intentional because I want this guy here to have zero trace. Okay, so that's basically my construction. Sigma mu nu obeys, its trace is exactly zero. So I split my gradients into a traceless part, the shear part, and the trace part, which is the bulk part. And this sort of gives me these two structures. Yes.
Could you explain again why we're doing space-like derivatives?
Oh, why we're doing space-like derivatives? Yes. So in principle, you write down derivatives of your u. But then you realize, so I'm writing down corrections to first order gradients to the energy momentum tensor, but I have my zeroth order equations of motions as the background that I'm expanding around. So remember that I said these equations here contain terms like this. So the zeroth order, that was one of the equations that I had to write down. So that means that when I write down a time-like component, I can replace it by the corresponding space-like gradient. So like in the diffusion equation where there was an ambiguity between space-like and time-like gradients, that's the same case here. I have to make a choice which one are the ones that I take as my independent expansions, and I take the space-like ones, just as the same way as I did in the diffusion equation.
Derivatives of the energy.
Yes, very good. So these are two possible terms that we've been writing down. You might object, okay, there could be other things, and Ule sort of points out there's another one here. Let's sort of write down u mu, d mu, and for instance, something like this would work. I have to suitably symmetrize it, and there would be a coefficient, let me call it alpha, and I can write this down. But then I have to remember that, okay, but what did I mean by energy density in the first place? And what I mean by energy density, well, it's fairly obvious in equilibrium. It's just the expectation value of the Hamiltonian of the system. But once I write down these corrections here, it's no longer obvious that sort of, if I just write down anything, that my energy density really is the expectation value of my Hamiltonian. So I have to make sure that that's still the case. And what that means is that I want to sort of impose that, sort of make this, I want to impose that whatever order in approximation I write down for the energy momentum tensor, if I take the time-like part of this, this always is equal to the energy density, or its eigenvalue is always equal to the energy density. This ensures that no matter what system I have, the co-moving time-like part of the energy momentum tensor, the Hamiltonian, the expectation value of this is the energy density, even out of equilibrium. And it's a choice, but it's a physically meaningful choice, I would say. So by sort of taking this choice here, you can see what happens to this term here. You already know that this term here, we calculated, you can look at this here. So basically what you find is that this, because the u mu sort of annihilates with this one, that term goes away. And this plate here just gives minus epsilon u nu. So it already fulfills the right-hand side. So what it means is that the projection of u mu on all of these higher order terms always has to vanish identically. And that means that this coefficient alpha has to be 0. So basically, fulfilled by choice of frame.
Can I ask a question here?
Yes.
Which is an advanced question, but I'm afraid this equation will disappear and then I can say something. There have been papers in the last year appearing that played with this and changed it by Kaufman and Bologna in an attempt to make first order Navier-Stokes hydrodynamics possible.
Right.
Is that physically allowed?
Okay. So yes,
a very
right.
strong point that this is very reasonable, and I completely agree.
Yes, I would argue it's very reasonable. Sure, you might sort of take the stance that I don't know what the energy density is, and if you don't impose this condition, you can actually write down first order formulations that are first order formulations of fluid dynamics that sort of obey causality. The issue that you get is that you have no longer a means of knowing what your energy density is. So you can write, if you give me an energy momentum tensor, I can tell you, well, what is the energy density of that thing? In these free frame sort of formulations of hydrodynamics, if they are given an energy momentum tensor, they cannot tell you what the energy density is. So while it's formally possible to do this, I'm personally not sure whether this can be sort of made useful in practice in order to solve initial value problems, let's say.
If I choose one of these frames that is non-standard frame, of course, with that, after having made that choice, I do know.
So I think what they find is that what you get is you get differential equations that relate the evolution of the energy density. So you get more equations, which are PDEs, which if you solve those, you can sort of backtrack and figure out what the energy density was to start with. It's not clear to me how you do this in a local manner. I think that's what I can say. So, right, I mean, it's my opinion, and may be wrong, but I'm sure that this at least works. that's what I can say. So, good. So basically we have these construction here. We know what terms to include. And the important thing to notice is that at first order ingredients, these are the two structures that you can write down, and there are no others. Okay? You might briefly sort of think, oh, but I have my metric tensor floating around, so maybe I can look at first order sort of derivatives of my metric tensor. well, these are Christoffel symbols. Christoffel symbols are not invariant under diffeomorphism changes. So the same way that you can't write a gauge potential in your diffusion current because it violates gauge invariance, often observable, you can't write down Christoffels in your energy momentum tensor because it's not gauge invariant. So that doesn't work. There are no terms involving first order gradients of the metric tensor appearing in this construction. Fine. And let's just see how I'm doing on time. So basically, you get this energy momentum tensor, and then the same way as before, you find that the energy momentum tensor that is sort of built up now has to be conserved.
There is a question on that.
Yes.
What's the equation in the box?
Yes.
Choice of frame.
Good question. So basically, it's a choice of frame because, for instance, think about if I had one more conserved quantity in my game, if I supplemented my consideration to a fluid that's charged, for instance, then you have, in addition to energy and momentum, you have a charge current, J mu. And then suddenly it becomes your choice whether you define your fluid to be co-moving or expanded around the frame given by energy density or by charge density. And this is something that we refer to as frame choice. In this case, when you have only energy density and you want an algebraic definition of the energy density, I think that's the choice that you basically are led to. But if you, for instance, have more conserved quantities, you have an arbitrary number of choices of frame. So yeah, it's basically, that's why it's called a choice of frame.
Does it always have complex quantities?
No, I mean, as sort of the discussion before sort of said, you could also sort of say that, okay, maybe I sort of use a frame where I want to sort of determine my sort of energy density dynamically through an equation. Then even in this case, you can sort of write down a different choice of frame. But the price you pay is that your energy density is no longer algebraic. So you have to solve PDEs to even know what your energy density is. Okay, so once we have our conservation of the energy momentum tensor, I said that without this term, what we have is the relativistic Oil equations. Once we stick in these two terms, these are nothing else but the relativistic Navier-Stokes equations. And if I play the same game that I played before, I sort of take the non-relativistic limit of this, out pop exactly the equations of Navier-Stokes that you find in any sort of textbook on fluid dynamics. So you get most of engineering, okay? Now, I'm not kidding. I mean, and again, sort of think about, we sort of needed 1.5 hours to get there, okay? So the input that sort of is required to get to the physics that you can describe with this is sort of staggering in terms of, okay, what do you have to put in? Symmetries and an EFT. And what do you get out? Well, you get out how to make an airplane fly, okay? How to do better forecasting. All of this comes out of that. Now, of course, okay, let me just finish that thought and then let's sort of get back to this. We can sort of continue on this program. And as you can probably guess, if we now write down terms of second order, third order, and so on, the sort of amount of terms that you can sort of combine from these building blocks becomes more and more complicated. I will just write down some things because I will sort of refer to those next. So at second order, okay, there are terms that sort of look like this. I'll write them down and then I will erase them and I'll talk about them for a little while longer. Plus, so let's just say 8 more terms. And then T minus 3, I will simply say 68 terms. I want to sort of make maybe 2 remarks. The first remark is that at second order, for the first time, you can write down derivatives of the metric that are gauge invariant, that contribute. So these are things that sort of come in with kappa R mu nu, where R is the Ricci tensor. And if you had started with a purely flat expansion in the first place, you would miss these terms, okay? Because they're just Ricci. Why would you write down a Ricci term if you're in flat space, okay? But for consistency, they are there, and they're important because it turns out that similar to the Einstein relations in the diffusion equation, this term kappa, even though it's a curvature matter coupling, will come in flat space correlation functions. If you don't write it down, you screw up your correlation functions, you'll get nonsensical results. So that's why it's important to include all the source terms properly in your derivation, otherwise you will screw up your correlation functions. The second thing I'll remark is that, well, the number of terms grow very strongly. So at leading order, we have 2 terms. At next to leading order, okay, you also have 2 terms. Then we get total something like 9 terms, get 68 terms. You can sort of try to count the number of terms, and it roughly goes like n factorial. It's very different if you wrote down only the linear terms. So remember when in diffusion we started out doing diffusion. So in diffusion to second order or higher order, we had the option of either having gradient of Laplace n or gradient of n multiplying Laplace n. This is a linear term because it's linear in the field. This is a nonlinear term because it sort of has n appearing twice. Okay. If you concentrate just on the linear terms, you find that the number of terms does not grow factorially because, well, you just add on gradients. So there's not a factorial number of terms that you can write down if you want to write n of those. But if you include the nonlinear terms, it grows factorially. Okay? This will become important when we discuss convergence and divergence of the gradient series expansion. Yes.
What are those angle brackets?
Yes. Okay. The angle brackets are basically a particular projector on the space-like traceless part. They are not important for what I'm going to say. It's a technical detail that I want to glance over, and I can give you all the details. They are on the indices. Yes. Everything is in the book. Of course. Good. So this construction is straightforward. It can, in principle, be sort of expanded to any order. In practice, a third order is where the literature stops. Okay. 68 terms are already pretty complicated. At fourth order, you can probably sort of guess there are hundreds of terms that you have to write down. Nobody has tried to sort of attack that problem. Okay, questions? Yes?
So you say you need to include the curvature for consistency once you get a second order. Does that imply you have to also solve the Einstein equations, or can you just not couple the matter to gravity in order to sort of turn off the curvature?
Yes, so if you're interested in flat space correlation functions, you do not have to turn on gravity. It's perfectly fine to sort of leave G as a perturbation, but if you sort of do variational sort of derivatives with respect to G, these terms will arise and they will sort of contribute in your correlation functions. And let me just sort of make a note that historically, that was how they were discovered in the first place, because if you write down correlation functions of the energy momentum tensor, it turns out there are a number of different combinations that you can write down, so there are a number of different coefficients that contribute. But if you don't include these terms, you don't have enough numbers to fix all of these correlation functions. So people were sort of defining parameters, like in the Kugeln relation, in particular this relaxation time, using, let's say, correlation function 1 and 2, but ignoring 3, or 1 and 3 and ignoring 2. And they got different answers whichever way you sort of did things. And the only way that you get a consistent picture is that if you include this term, and then suddenly all of them sort of give the same answer. I'm going to write down this guy for now. Okay. So the rest of the lecture, I want to sort of say something about how we define things like pressure out of equilibrium. Then I want to briefly talk about causality and causality violations. And then I want to sort of get started into sort of doing attractors, which is sort of the next big topic that we're sort of getting into, in particular for next lecture. So let's do one of these at a time. If I stare at a combination of the 0th order and the 1st order expression for the energy momentum tensor, remember that what we are effectively doing is we are sort of writing down the expectation value of the operator for the energy momentum tensor in the gradient expansion. So we write this down as T mu 0 plus T mu 1 plus and so on and so forth. If we neglect all the derivative corrections, what we find is that the energy momentum tensor gets expressed in terms of the energy and the pressure, and this really are sort of the energy and the pressure that correspond to the expectation value in equilibrium. Okay? So meaning that if I sort of write down, in particular, let me write down the trace of the energy momentum tensor, then if I look at the trace of T mu nu, the trace of this gives me minus epsilon from here, and then it gives plus P times the trace of delta. Delta is this combination here, so the trace of delta just gives me the trace of the metric tensor, which is just, well, okay. So depending on the dimensions.
Do it in the local restaurant, right? That's just true.
Yes, you can do it in local restream. It depends on the dimension of the problem. If we are in 3 plus 1 dimensions, this is just 3. So then we just get 3p. This is just the part that's coming from the ideal part here. And again, if you sort of truncate the system, then this is just the trace anomaly of the full energy momentum tensor. So left and right hand side match in equilibrium. Okay, so really, in some sense, there's a one-to-one correspondence between doing this expansion in gradients and an expansion around equilibrium. I will sort of add a possible loophole to what I just said, maybe on Thursday's lecture. But for now, let's just sort of stick with this. Now let's look at the yes, when I say equilibrium, essentially always I mean local equilibrium, except if for some reason I were to talk about hydrostatics, which I ignore for these lectures. So yes, basically it's always local equilibrium. So let's look at the trace of this guy here. I said that the way that I construct this is that the shear path is manifestly traceless. So sigma mu was defined to be 0. So the only contribution comes from this guy here. So then I have minus, I have again the trace of this delta, 3 zeta d mu mu. And you notice that, or you can sort of notice already here, the structure of this equation sort of matches with the structure that we have, the pressure in the leading order. So that effectively, really what this bulk term here does, it's correcting, it's adding a correction on the pressure. So we can write this term here also by, let's leave it for the moment like that. A plus higher order. So effectively what's happening is that we get something that sort of looks like minus epsilon plus 3 P effective, where P effective is the pressure, which I said here, this is really the equilibrium pressure, which is just a function of the energy density. And then we have minus corrections such as zeta d mu u mu plus higher orders. Now, away from equilibrium, there is no longer the trace of the operator of the energy momentum tensor no longer will match with the equilibrium trace anomaly. Okay, so that's not something you can expect. However, you notice that whatever violation we have out of equilibrium from the equilibrium trace anomaly in the operator, you can always sort of plug into this effective pressure. So what I'm saying is that you can sort of consistently define the P that's appearing in our sort of expansion to be always related to the energy density through the equilibrium equation of state, because all the deviations you can plug in into all the rest. So to reiterate, we go away from equilibrium. There is no reason sort of believe that we have an equilibrium equation of state, but we can write the non-equilibrium equation of state as the equilibrium equation of state plus corrections, and the corrections sort of reside in all of the other terms that we have sort of captured in the process. So it's a sort of slightly touchy thing, okay? So there is no longer a temperature in a strictly thermodynamic sense, but there's a pseudo temperature that takes the role of it. Okay? So out of equilibrium, the energy density is always the expectation value of the Hamiltonian. Out of equilibrium, that's a perfectly well-defined procedure to define. The pressure is given by the equilibrium equation of state defined with this out of equilibrium energy density. And the effective pressure, that's the thing that really sort of controls out of equilibrium evolution of the system, is given by the equilibrium pressure plus corrections. And I will call the corrections just pi. The pi is this stuff plus all higher order corrections. So that defines fluid dynamics out of equilibrium in a rigorous way. And it's sort of important to sort of realize that, okay, when you do non-ideal fluid dynamics, so fluid dynamics beyond zeroth order, you're effectively always away from equilibrium. So strictly speaking, there never is a temperature, there never is an equation of state that's equilibrium. But there are all these sort of pseudo relations that you can use when you sort of set it up this way. And we'll push it pretty far, okay? So we'll eventually sort of take this not close to equilibrium, but actually very, very far away from equilibrium. And because of this construction, at least formally, we are perfectly fine. Let me say the one thing that will destroy the whole framework is if for some reason, okay, I haven't really sort of, this is one important point actually. Okay. So I said that I want to sort of define my energy momentum tensor by the time-like eigenvector of basically this whole expectation value of the operator of the energy momentum tensor. There are situations where the expectation value of the energy momentum tensor does not have a time-like eigenvector, and then the whole construction breaks down. Okay. But usually these are really pretty extreme deviations from equilibrium. But you can write them down. There's an energy momentum tensor, but it has no local response. And then this whole thing fails. So keep that in mind. Okay.
Are there any situations known where this might occur?
Where it might occur, where?
In practice?
So it occurs if you, for instance, look at strongly coupled shockwave collisions in ADS CFT, for instance. There's a region on the light cone that violates local rest frame. Is it important? I don't know. Does it have observable consequences? I don't know. It's simply not studied. There is no local rest frame. There's no. But there is there is eigenvectors, but they're not time-like. They're typically complex. And you can write down things where this actually happens in practice. Right. Yeah. So I would sort of simply say that, okay, if that happens, it's bad. I'm not sure if it's fatal to any setup of fluid behavior. But basically what it means is that the epsilon that we have here is no longer the expectation value of your Hamiltonian, because somehow that relation breaks down. Again, in situations where we have control over the quantum field theory, typically, for instance, in ADS-CFT, what you find is that these are regions in space-time that are localized. So they sort of open up, there's a violation of local rest frame, and then they close again. And all around this, fluid dynamics is perfectly fine. And even if you look in that sort of thing here, and you do funny things like you take the real value of this operator or something like that to get to the eigenvalue, you basically sort of get pretty good sort of approximation to what's actually happening. But strictly speaking, really, you've lost your local rest frame. So it's more of a conceptual issue than anything else. But yeah, I just reiterate that it's just not studied. People have not looked at it.
And the picture of the definition of pressure.
Yes.
How are you doing with the usual thermodynamic equation?
So
Please redefine the definition.
right. So the question is how you sort of, you want to sort of ask how the, okay. So the question is how these goes together with the usual thermodynamic relations. So the equilibrium part of the pressure, the P that you see appearing there, that is just fulfilling the usual thermodynamic relation. So you're asking about out of equilibrium?
Yeah, so till now you have never talked about that in talk. So will I
Right.
become our usual thermodynamic PP is SE in the post-thermal relationship in this technique?
Right. So for the equilibrium part, obviously by construction, and out of equilibrium we'll have corrections because you have an out of equilibrium entropy, and this fulfills some notions of thermodynamic consistency. In the cases where we can actually check it, that usually are cases that have a holographic dual, that we can map the entropy to the area of a black hole in a higher dimension, and there that is something that we have a geometric meaning even out of equilibrium, and we can check that this sort of relation sort of makes sense. But very far from equilibrium, I think it's not clear whether this construction really sort of has a notion of thermodynamic consistency, positivity of entropy, or things like that. But whenever you can map it to the area of a black hole, you have some meaning of, you can push this, okay? If you don't have a black hole dual, it gets much more tricky. Okay, good. Fine. So I just want to sort of hark back on this point before that. If I sort of include the sort of first order correction to the energy momentum tensor, what I have effectively are the relativistic versions of the Navier-Stokes equations. And so, oh, that is the wrong marker. Where did I put my good marker? Let me see, maybe this one is. And basically, I just wanted to point out that all of these issues with causality that we've seen in the diffusion case essentially comes back in this regime here. So let's see. So basically, so essentially what one has to do is you sort of do a Fourier analysis basically saying epsilon and u mu go like e to the minus I omega t plus ikx. You plug it into the equations of motion, and unlike in the diffusion case, you find more than one mode. You find that there are so there are 3 modes, depending on your counting. There is 2 sound modes, which sort of roughly go like omega squared is CS squared K squared minus I gamma A cubed something. And there are 2 because we have omega squared is something, so they're plus and minus, so there's a left move and a right move. And there is 1 shear mode, which basically has the property that omega is basically given by, let's see if I can do this here, it's basically given by minus I, gamma beta K squared. So it sort of formally looks a lot like the diffusion mode that we had before. It has exactly the same structure. And this gamma eta here is basically just the shear viscosity coefficient divided by epsilon plus b. And because it has exactly the same structure as the diffusion mode that we discussed in last lecture, you can figure out that, okay, this relativistic version of the Navier-Stokes equation has modes that propagate faster than the speed of light, so it violates causality. Then you can sort of get back and say, oh, but these are only the high momentum modes, which we are not, which we did not mean to capture in this sort of framework anyways. We said, okay, that's fine, but then again, unless you have an analytic solution to the relativistic version of the Navier-Stokes equation where you can actually project out these offending high momentum modes, you are left with trying to solve this on a computer, and then the causality really hits you because it sort of means that you have exponentially, you have instabilities in trying to solve the equations of motion. The real sort of is exactly mirroring the situation that we had for the diffusion equation. And you can ask, well, can you use the same tricks that we sort of used to stabilize or UV complete the diffusion equation? And the answer is yes. So you can sort of write down, so one way that people sort of write this down is that, let's write down T mu nu as T mu nu 0 plus pi mu nu plus delta mu nu pi. Okay. So what I've done is that I've said that, okay, rather than sort of writing this down as first order, second order, third order, and so on, I write it as corrections to the ideal case. This guy here is traceless transverse, so this is the shear stress, and it includes this term here plus higher order stuff. And this part here is the term that is the bulk stress, so it includes that term plus higher order terms. So this way I don't have to write down plus dot dot dot. Everything is in terms of these, and that decomposition is exact as long as I have a local restroom. So the leading order, this pi mu nu is just minus eta sigma mu nu, but in particular, I can have higher order terms. Remember, we played these games with the diffusion equation. We wrote down higher order terms just in purely spatial gradients. We found that, okay, this didn't work very well. And then we sort of said, oh, but we have this ambiguity, time-like, space-like. We can trade space-like derivatives with respect to time-like derivatives. We do exactly the same game here. And I conveniently erased the term that I want to sort of point to. But there was a term here that was something like, let me write it down, minus r pi eta e sigma mu nu with this funny projector. That's just the usual, that's some version of the expansion. But then I can say, oh, but eta sigma mu nu is just the object I have on the left-hand side. So let me sort of try to do this kind of resummation that I said we can do for the diffusion case and stick this in such that we get an equation where pi mu nu now appears both on the left and the right-hand side. This clearly changes the character of the equation, and we can look for the corresponding modes or the change in the collective modes of this system. And really, the only thing we have to do is we have to sort of analyze the collective mode structure of this guy, so we can do a Fourier transform of this directly. If we do a Fourier transform of this, we have, let me just write it as pi. I will sort of be very, we can write this minus tau pi, and then this is something like a time-like derivative. So basically, it brings down minus I omega. We get plus I omega pi. So that means that this equation here says that pi is sort of minus beta sigma divided by 1 minus I omega. And hopefully that sort of structure should look kind of familiar to those of you who were listening to yesterday's lecture, because effectively what you get is you get 1 more power of omega in the dispersion relation. This will change the dispersion relation for the shear mode to a quadratic one. That we now have 2 solutions, one which is in the low momentum regime, just the usual diffusion mode, the shear mode, and the other one which will be another mode. And you can sort of see what the other dispersion relation is just by looking at this equation here. Note there's a hole in this located at a particular value of omega. So this has a mode. Now I can actually call it a non-hydro mode. And it's located at omega is, if this is 0, and regular the size is minus I over tau pi. So remember, we had a dispersion relation just like this for the diffusion case, but the tau was just this parameter that I had in the diffusion case. So long story short, the issue with the violation of causality for full-blown relativistic Navier-Stokes is exactly the same as for the diffusion equation, and we can borrow the same tricks, which in the context of hydrodynamics sort of go by the names of Maxwell, Navier, and later on Israel and Stewart. And you can sort of basically sort of resum this infinite order gradient expansion to sort of produce an equation that sort of introduces this new mode in the system. So we do a UV completion of the system. The price we pay is we have a new excitation in the system, this non-hydrodynamic mode, which is not going to 0 as the wave number becomes small. And that has the same effect. It cures the UV problem. It gives us a stable causal evolution of the system. So you can sort of take these equations in motion, put them on a computer, and solve them. I have 2 more minutes. Let's see if there's some questions. Yeah.
What were you calling the next one? So this is called Maxwell.
Right. So various people have worked on this. Okay. I sort of alluded to the fact that Maxwell, I think, was bothered by the diffusion equation not respecting causality. He was sort of the first to sort of thought about this. Later on, in particular in the context of fluid dynamics, it was picked off on by Cataneo in the 1940s. That's one version. A little later then it was picked off by Müller, 1960s or so, and then later on by Bernard Israel and Stewart in the 1970s and 80s. And really sort of it is reiterations of this sort of theme that we start off with. Well, basically sort of you recognize there is an issue at high momentum, you try to regulate it, and the way you regulate it is that you sort of rewrite equations such that it becomes something that sort of, well, for instance, introduces this new, now dynamic degree of freedom here. And once you do that, you can basically sort of stabilize the system such that the UV becomes up. I mean, physically, it's fairly straightforward to see what's happening, right? I mean, if I don't have this term here, if I change somewhere in my system, okay, I have a universe, and I don't know, over in Pluto, I sort of do something, I change the fluid velocity of the velocity of Pluto just a little bit. Then this thing here will be the gradient of the fluid velocity. It will instantaneously know about that I changed the fluid velocity on Pluto here on Earth and also over in Alpha Centauri. So you have instantaneous signal propagation because the pi knows about what you did without any sort of time delay whatsoever. That is are causal, and that's the root, the physical root of the problem. Now, if you sort of write the second term here, what it says is that, okay, you change this side here, but that sort of change in the pi takes some time. This is a time derivative. It takes some time before it feels that signal. And that sort of time delay is effectively given by this new parameter, tau. So that we sort of basically put the finite cutoff on your signal speed, and that will sort of make the theory causal in case the ratio between these two numbers is small. Let me maybe sort of make two more remarks and then sort of finish with today's lecture. The first remark I want to sort of say is that, so the signal speed will be finite if the ratio of tau pi over eta is larger than some critical value. Now you can calculate this value of these transport coefficients in microscopic theories. Okay, the tau pi is, and I deleted this. The tau pi is just a second order transport coefficient. It's just a second order gradient term in your expansion that you've rewritten. So there's a Kubo formula for this, and because of this, you can calculate it, and you find that the ratio of these two numbers is smaller than this. Is such that the velocity is smaller than the speed of light for all systems, for most systems. I know of one counterexample, which is in 2 dimensions, but in sort of, for instance, in 3 dimensions, there's no known counterexample for this. You always get final signal propagation speed if you plug in the microscopic values for this. Even though, in principle, the microscopic theory, you shouldn't care about what the UV does because you're expanding around very small momenta. So there's no guarantee that this has to work, but it is kind of taunting to sort of. So for instance, you can look at the signal speed, for instance, in holographic duals as a function of the dimensionality, and you find that the signal speed saturates at 1, exactly 1, in the limit where you go to 1 + 1 dimensions, where sort of fluid dynamics is almost not defined at all, but it sort of doesn't saturate at a different number, but it's exactly the speed of light. So it's kind of mysterious why this happens.
Always less than the speed of light.
It's always less than the speed. Yes, yes. So it's always less than the speed of light, except for one countdown example, where I think the issue is that this number here, the tau pi, is actually negative. And this is also a holographic dual, and I'm not sure whether the corresponding theory is physically realizable, but there is one named counterexample. Good. So with that, I want to sort of end today's lecture, and tomorrow I'll really sort of go into the business of hydrodynamic attractors.
Any more questions before we let him go?
Yes, please go ahead. Question. Yes.
Oh, okay. So on this causal flexibility analysis, usually one on top of a Indian global.
Yes.
More generic situations, then this kind of formulation is causal.
Yes, you are right that most of the analysis are done in the background. That is sort of global equilibrium. There are some cases where that has been done more generally, where you have some non-static background, for instance. My understanding is that in these cases, typically this also works, but I would have to sort of remember myself exactly what was included and what was not included. Typically, if you go to more complex background solutions, the analysis gets more complicated, so people tend to throw away more terms. But there are some checks even away from just depending around globally.
Can you please explain again how to get rid of causality? I mean, how to make it causal again?
Yes. So basically the way it works is that, so if we have just this part of the,
Repeat the question.
oh yeah, so the question is how does this construction make the theory causal again? So if we don't have this term here, just this part here, we get a shear mode that has this dispersion relation, which has the problem that omega is quadratic in K, so that means that the group velocity is linear in K, so it grows without bound as K gets very large. Now that include the second term here, the dispersion relation of pi gets to be the one we had divided by this thing here. So that means that the shear mode dispersion relation sort of becomes something like this, where you have 1 minus I omega tau times I omega is gamma eta k squared, because you're sort of multiplying by this denominator here. So you get a quadratic equation in omega. So then let's sort of take omega to be very large, omega to be very large, and k to be very large. Then basically this equation here means that we have omega squared tau is gamma eta k squared. That means that omega is plus minus square root of gamma eta over tau k, and the group velocity is the derivative of this guy with respect to k. So what we get is that this is square root of gamma eta over tau. So if this ratio here is smaller than 1, the theory is causal.
Another question.
Yes.
If including higher orders from gravity affects transport coefficient calculation, can you please explain in what cases, ignoring those corrections?
Yes. So, right. So for instance, we have the second order contribution to the energy momentum tensor, and it includes a term that sort of write it in a different form again. So it includes a term that looks like this. So there's a second order contribution that includes this transport parameter tau pi. And in order to fix tau pi, there are various ways we can do that. Okay, so we can, for instance, look at the shear mode dispersion relations. So this relation here, but now extend it to second order. So include all second order terms. Calculate that in fluid dynamics, calculate it in the microscopic theory, and check that the two of them sort of have to be the same. And do that at the sound mode. And then we can also look at nonlinear evolutions. It's kind of quite tricky to explain. We can look at, so this is not nonlinear evolution. And I feel I'm not able to sort of give a concrete answer in a few minutes. So I think what I want to say is that, okay, so what you find is that you get sort of different results, in particular in these two, if you don't include these curvature corrections. If you do, both of them sort of give the same result. And I think the person should just email me, because I can just point to the corresponding references to point out what the technical sort of realization of this is. Okay, thank you very much, and I'll see you tomorrow.